Okay. So I'm going to talk about each different kind of wheel in a little bit more depth. Most teams will use the same wheel on all parts of the robot, but you don't necessarily need to. You can combine a scroll wheel with an Omni wheel or whatever you want to do. The first type of wheel I'm going to talk about is, they're called Omni wheels. And so what you have is, you see here, there are rollers on the wheel, which allow the wheel to slide left and right on the ground. But if you were to spin the wheel forward or backwards, it would move in that direction. So in order to control where these wheels go, we'll take the example of the wheel directly parallel to the ground. So if I were to spin this wheel, it would spin like that, and move that way or that way. And the rollers will allow it to move vertically. And so if we want this wheel to go, have this velocity, let's say. The velocity would be what we calculated in the first part. But if, for instance, we wanted it to go there, what you might realize is that the rollers will take up all the speed in the vertical direction, and the rolling of the wheel will account for all the speed in the horizontal direction. Now, there are some very fancy Omni wheels, like the ones made by Honda, that have the rollers powered, but most Omni wheels don't. And so, for the most part, you're just going to want to ignore the Y component of the vector. And so, but the X component is going to be what you want to apply to your motor value, because that's how much the wheel is going to actually spin and move. And so, your motor value is simply R plus theta from converting from both coordinates. Now, the problem is most people don't want to put their Omni wheels directly horizontal. In fact, most designs for Omni wheels, going back here, most of them have them at 45-degree angles or in a triangle kind of configuration. So the thing to realize is if we rotate the Omni wheel, none of the physics change. X is still equal to R cos theta. The difference is it's a little more difficult to find theta because it's not just as simple as the angle of the vector. What we need to do is find the angle of the vector and then find the angle that the wheel is oriented at. And then in this diagram, the angle theta would just be blue minus the red. And so mathematically, theta equals the angle of our velocity vector minus the angle our wheel is pointed at. And then the motor value is simply the magnitude of our velocity vector times the cosine of x. Okay, so before I go on the other wheel types, something I want to talk about is with the kind of wheel velocities you can generate, it's very easy to get motor values that can't actually exist. You can easily try to set one of your motors to 2 or -5. And if you were to do that on our robot, as you might know if you've been doing programming, motor values are between -1 and +1. That's their range. And so if you try to go outside that, you try to set your motor to 2, it simply chops that value off and says, okay, your motor's going at 1. And the problem with doing this in an Omni Drive situation is that we want the motor values to stay always proportional to each other. But the trouble is if you chop it off, that value is obviously not going to stay proportional. So, an algorithm for rescaling the values back so they're within the correct motor range while keeping it proportional would be, first of all, we don't need to do anything if they're already on the range, obviously. Otherwise, we need to find the max absolute value of any of the motors that we're trying to set. And the absolute value, simply ignore negative signs. So if you have absolute value of -100, it would be 100. So, and then we divide all the motor values by this number. So as an example of this, these are pretty ridiculous values to try and set your motor to, but if we were trying to set it to negative 10, 20, 40, and negative 50, the maximum absolute value of any of the motors would be 50, because you want to chop off the negative signs, and that's the largest one. And so if we divide all the values by 50, what you might notice is these are the results we get. And these are all directly proportional to each other in the same way that these are. Negative 10 times 2, or, yeah. If you multiply negative 10 by negative 2, you get 20. If you multiply negative 0.2 by 2, you get 20. But all these values have been scaled back to the range of negative 1 to 1. Okay. So Mecanum wheels. If you haven't seen a Mecanum ball before, they are really, really cool. The most prominent team who have them last year was probably Team 188, although a lot of teams use these kinds of wheels. They're kind of like Omni wheels, but the rollers are oriented at 45-degree angles to the ground. So I wish I had a video of how they drive, but basically...
188
have? Yeah, 1310 also uses those.
So one of the robots has a giant one.
I think I remember that too. Yeah, so anyways, Mecanum wheels, they were really, really weird. When I first saw them, I thought they were scary voodoo magic. But if we were to think of how we might drive with them, these rollers, I'm sorry for the bad diagram, it's like these rollers have an axle like that, so they can spin in this direction. And so if you were to put this Mecanum wheel on the ground, it would just roll in that direction because the rollers would take out all the slack and we would need to turn. So the idea here is rather complicated. What we need to do is take our original velocity vector and we need to rewrite it as a sum of two other vectors. And the problem is we don't know what any of those vectors are going to be, so we can't perform a simple subtraction. But there are some things that we do know. For instance, you might recognize that this vector here, which is, this vector represents how fast the wheels are, or how fast the rollers are rotating. And this vector will represent how fast the wheel is actually spinning. So if we add those two together, we want to get the final velocity. And so the wheel roller is rotating needs to account for the entire x-coordinate of the velocity vector. Because the wheel is oriented directly up and down, it doesn't have an x-coordinate. So this here, the x-coordinate of the red vector, is going to be equal to the x-coordinate of our green vector. And the other thing that we know about Mecanum wheels is the rollers are oriented at 45 degrees. So what that does is it makes this an isosceles triangle. So the vertical coordinate of the red vector is also going to be equal to x. And so now what we know is this whole distance is equal to y, and this distance is equal to x. So if we want to find this distance, is y minus x. So Mecanum wheels, compared to the other forms that you could do, are really, really simple to program. Conceptually, they are quite difficult, but in terms of the actual code you write, they're a very elegant solution. And if we were to make the roller space the other way, which you need to do if you have a Mecanum drive, it's simply like inverting the x-coordinates. So anywhere we see an x, we make it negative x. And so the overall result would be y plus x. So the motor value for a Mecanum wheel is either your velocity y coordinate minus your velocity x coordinate, or you add the two coordinates together, depending on which way you want the roller to